Hi, my name is Matt Maxwell, and I'm a product manager for Tektronix Spectrum Analyzers. And this is a quick how-to video for testing a Bluetooth device for first power on. So to do that, you need to have a decent RF environment, either using an antenna in a relatively quiet space. In this case, for this device, I'm going to use this particular demonstration board with an RF connector on it. There needs to be some test port, some way of getting the signal into the spectrum analyzer. And the analyzer I'm going to use here today is an RSA 607A real-time spectrum analyzer. Now this is a USB controlled analyzer that's being controlled from the SignalView PC software. So let's go ahead and get started. So this assumes I have a good setup to my Bluetooth device, maybe an antenna port or a good clean RF environment where I can use an antenna to pick up the wireless signal. I'm going to perform some basic spectrum measurements here. So I happen to know the center frequency where the Bluetooth is transmitting. If I didn't know where the center frequency was, I could always adjust the span to maybe a wider span. So now with a 100 megahertz span at a 2.45 gigahertz frequency, I can see everything in the ISM band. That would just allow me to pick up the signal. I'm going to go back to the 40 megahertz span because that's the real-time span for the analyzer, and it's plenty of bandwidth. Bluetooth low energy, for example, or even a test mode for Bluetooth basic or Bluetooth enhanced data rate could be put in a test mode and look at a particular park frequency. And then I have multiple traces that I can turn on for the analyzer. And I can even reduce the span to a 10 megahertz span. And that's approximately a division maybe at the 3 dB down point. So I can visually estimate that bandwidth to be about a megahertz. And I know that the bandwidth, the symbol rate for a Bluetooth signal is 1 megasymbol per second. So that checks out. If I want to add additional markers to look at the peak power, minus 15 dBm, I can start to do that. I can add another marker and kind of look at a 3 dB down-ish point. So there's about 412 kilohertz, maybe 1 dB down from the peak. But I could play around with that a little bit manually to do a channel power measurement. I also have an automatic channel power measurement if that's of interest. Really, the important part there is to make sure the device is turning on, it's transmitting correctly. It's approximately what you expect. You probably don't need to go into any more detail than that. But that's a good first pass. Everything looks like it's working correctly here. The next thing I'd like to show you that might be interesting is a real-time display called a DPX display. Now DPX stands for Digital Phosphor Spectrum. So that comes from the old days of using cathode ray tubes and oscilloscopes in those days. Oscilloscope users appreciated the CRT tubes because it gave them some idea, some insight into signal behavior, because once the electron beam trace went over a part of the screen, it dwelled on that part of the screen and became more bright. If it spent more time there, it was more bright. Less time, it was more dim. We try to approximate the same kind of insight here with the real-time display, where now instead of brightness, I have the color indicating the signal density over time. So the red colors mean signals are happening more often, and the blue colors indicate the signals happening less often. So you can imagine if I had a glitch here, if I had a problem, I can see this with a real-time display, with a DPX display, where I might miss this with a conventional analyzer. So good troubleshooting capabilities there. The next thing I'd like to do is show how that signal behaves over time. So here I have again the selected displays. Each of the measurement folders contain a different set of displays. In another video I show the Bluetooth analysis themselves, where I'm doing the demodulation of the Bluetooth signal, which is helpful to characterize the module, maybe useful for troubleshooting as well. But here I'm going to add a time overview and a spectrogram display, and I'll explain what these displays all mean here in a second. So now that the instrument's drawn the displays, I've got the time overview, upper left-hand corner, showing the amplitude versus time display of the measurement. I've got a spectrogram which shows the time versus frequency, and the color indicates the power. I've got the DPX display that I just described earlier in the regular spectrum display that we used earlier. This is helpful at first turn on, again, just to take a look to make sure things are working correctly. So a very useful thing to do here in the time overview is to start to increase the length of time that I'm analyzing the signal for. I want to make sure I capture at least one burst of signal, at least one or two complete bursts of signals. So now I look at I'm having a 2 millisecond scale analysis time. So the scale here is 2 milliseconds with the RF envelope power with the power readings on the vertical axis. And then I'm going to turn on the level trigger. So I go to the trigger menu, turn on the trigger, and set the level to minus 20 dBm, so something around the level that I would actually capture. And so now, if I stop the analyzer, I can see the time domain view here with the time overview, still seeing the spectrogram and DPX displays. The DPX display, interestingly, is on a parallel signal path. It's not affected by the trigger, or it could be, but it's not in this case the way I have it set up. And then the spectrogram is interesting because it's showing me, if I make that large, again, this is time versus power, it's showing me in 2 millisecond blocks of time. Each tick mark on the right-hand side indicates 2 milliseconds. It shows the power, the signal history of that Bluetooth burst in this case. So this would be a Bluetooth signal in a test mode, bursting repeatedly, Bluetooth low energy signal in this case. And I want to be able to look at that to make sure things are working as I expect them to make sure the behavior is what I expect. And I can even use the spectrum display here to help out a little bit and show a spectrogram trace where the marker reading here in the spectrogram and the saved data here automatically updates as I drag it through the spectrogram, so I can get more insight into the signal history over time. That could also be helpful if you're trying to find a hopped Bluetooth signal. I can look at the spectrogram and see everything within the 40 megahertz bandwidth or even a wider bandwidth if I want to use that and sweep across. So hopefully that's been useful for you, so you get a basic idea of how to check a Bluetooth device at first power on test. And I thank you for your time.